modeling something much less complicated than the last one. I'm going to be modeling a desalination process known as osmosis using OpenFOAM. So this is the most basic way you can model a membrane process, which is what forward osmosis is. You have a cross-flow top-to-bottom channel. The bottom channel here is a feed from a reservoir such as the ocean, which you want cleansed or desalinated. And it has some constant amount of salt mass fraction in it. We're not treating any kind of like biomaterial in this model. The top, top channel is a solution that you're going to be pumping through your system that has an artificially high amount of salt in it. It's usually some sort of molecular compound in a gas matrix. There's many kinds. Won't go into it. But one effect happens is because your draw solution is so much more salty than your incoming feed solution, you have an osmotic pressure difference, which drives flow, water flow, from your feed chamber into your draw chamber without any hydraulic pressure having to be applied to your system. So it's very low energy, energy efficient. Yeah. Oh, and because of this, you can model the water coming from the ocean as relatively having zero mass fraction, which makes computation easier. Okay, so as with any flow model, you have, for water, you're going to have a continuity equation and an Navier-Stokes equation. Because we're dealing with water, this shear viscosity term is going to basically contract down to an incompressible case. The important thing with this model is the diffusion convection equation. So we have a time derivative. The second term is a convection term. And the third term is a diffusion term. And this is going to allow a mass fraction of salt to be included in each control volume of the flow field. And what this is going to, in effect, do is create a change in the variables within that control volume. Pi is osmotic pressure, we have viscosity, diffusion term, and rho here. All are affected by this mass fraction MA, which is quite small. I think the highest case we're going to run is like 0.09 as a percentage. Or as a decimal, sorry. So what this in effect does is create a weakly compressible case. So this mass fraction is not going to cause molecularly the molecules of water to be able to go closer or farther together. The flow is still going to be incompressible. But we have to instantiate flow change due to this mass fraction. So it's known as weak compressibility. Okay, so initially this kind of, the solver used for this kind of system was a simple and piezo kind of coupling. I don't know how much you guys know about OpenFOAM. I think Dan's going to go into those later today. Since has updated this to a Pimple algorithm. So you basically just predict momentum, which instantiates like a U field using initial variables, and then you're going to iteratively solve the pressure and the salt transport equation until they match, and then use those to predict the next velocity equation, and you're going to repeat that until everything matches, and then you're going to go to the next time step. It's important that the salt equation is solved first before the pressure, because some variables in the pressure depend on the salt, and that's especially important for the velocity because the velocity term, the velocity equation in this solver, is dependent on mu, which is directly dependent on ma. So every time you're going to have a different mass fraction gradient, you're going to have a totally different mu. Okay, so this is the basic boundary conditions. Nothing really special on the walls. It's kind of just zero gradient, zero velocity. This profile here for the velocity is parabolic and actually uses the SWAP 4 foam that was mentioned earlier. Pretty simple implementation. The membrane has the special boundary conditions. It has an optional slope velocity, which I'll show you later, and a special gradient for mass fraction the pressure is a zero gradient, just like all the walls. Okay, so now we get into the actual membrane. The kind of membrane used for fluoride osmosis, if you look in the upper right corner, has a thin active layer which basically just models or allows water convection through it and rejects salt ideally. If the pressure gradient is very high, then you can get backflow through those channels. You can also get some sort of capillary effect where salt's just going to randomly pass through it. You could also have defects in the membrane that will allow salt passage. So if salt passes through that membrane from the draw to the feed side by accident or because of some sort of defect, then you're going to get an effect called ECP. That's external concentration pressure, or polarization, sorry. And what basically happens there is you're going to have a bunch of salt molecules that are forced against the edge of the membrane because of the main draw from the feed to the draw side of the water. So that will basically stop some water from going through the membrane and cause a concentration buildup of salt right here. Alternatively, you have ECP on the draw side, which means when water goes through the membrane, as it exits the membrane, it's going to dilute the salt feed right at the edge. So between these two effects, the overall osmotic pressure, high bulk, is going to be decreased because the flows think there is less salt, or there's less of a gradient between the overall draw. The inside the membrane, the porous layer, which basically stops the active layer from breaking, it's like a scaffolding, allows flow through it, but is not a very convective material. So as soon as water passes through this active layer, it effectively gets trapped right here, and the draw flow cannot wash it out. So you get a strong concentration of water right here that really dilutes the draw solution. So over this one little membrane part, you're going to only see about this much effective osmotic pressure, and your ability to transport water from one side to the other is drastically decreased. So research in this kind of membrane area is making porous support layers that allow convection through it. Or if you can get rid of those support layers altogether, that would be ideal. JS and AW are the fluxes of salt and water through the membrane. You can see the salt flux is due to a concentration difference, and the water flux is due to a osmotic pressure difference. So this is a more mathematically in-depth version of the two fluxes. Not that important. This U slip is the optional slip boundary condition you can have with velocity in the membrane. If you don't want that, if your membrane in modeling doesn't really have a slip condition, or you just don't want to put it in for like an idyllic case, then you can just set it to a zero vector like the walls. And this is the mass fraction gradient that is put on the membrane. All these Greek symbols you can see are kind of just known values for the flow at that point. Not very important. That's a generated case. You're going to see a lot of MA permeation due to capillary effect because the cross flow is very low. The water is basically just sitting there, and over time, salt's just going to force its way through. If you have any kind of high flow, that's going to be very low permeation. And you can see the ECP in the solution due to the water going through. So, okay, that's basically all the membrane stuff. So, the file system for this kind of solver. So you're going to have a main solver, which is the C file, and it's going to call on all these H files in order to help solve it. So the create fields file basically just instantiates all the fields. It allows you to start computation on a grid that has variables attached to each point. Without it, you would probably fail right away. The solver would just get a massive error. The U, P, and MA equations are all within that pimple loop I was showing you earlier, the solver loop. And the MA continuity is run after each time step to ensure that, basically to account for all the mass within the control volume and to make sure that boundary conditions aren't being violated. main folder Tim mentioned earlier. It's basically just to link your whole file system to the OpenFOAM library, so you can call it from any kind of case folder. So here's a case file system. You're going to have a 0 file with all your field variables in it and an order file. If you do not have an order file, your quality of life will decrease drastically. Have one. There's a system folder, and that controls all your time variables, all the ways that you want to discretize portions of your equations, like mathematical chunks of your equations. You can specify like Gauss linear, whatever you want for each of those. Your constant folder is going to have all of your mesh components and your properties of transport, like what constants to do with your equations, and any kind of constants you want to grab from the library, such as gravity. You can also implement turbulence properties, but in this kind of case, when your crossflow is half a meter per second, you're going to have a line of case no matter what, so there's no real point. Unless you choose like baffles or flow baffles to increase the turbulence. That's not going to be an issue. So this is a picture that I put on here without putting on a scale. Sorry about that. Basically, you're looking at the white thing is the membrane, the blue is the draw channel with idyllic 0 solute, and the red is the draw flow with some constant amount of mass fraction. I think here it's 0.01. And you can see there's a gradient where the water is being drawn through and diluted. Since this is a relatively high crossflow case, there's almost no salt permeation into the feed solution of the blue thing. So you're not going to see a kind of color gradient there. Not as exciting as the digestion. Okay, so